Here is the difference in one sentence. Microservices divide an application by what it does. Cells divide a platform by which users, resources, and failures belong together. They are two different boundaries, and a mature system can use both at the same time. Imagine a food delivery company called QuickBite. Instead of one enormous program, it has separate services for customers, restaurants, orders, payments, and delivery. Each service owns a business responsibility and can be changed or scaled without redeploying the entire application. That separation helps teams move independently. The payments team can release payment code while the delivery team scales driver matching. So microservices answer a very useful question. Which code, data, and team should change together? But that is not yet a customer-isolation boundary. In production, QuickBite might run a shared order service fleet, a shared payment service fleet, and one large orders database. Customers from Chennai, Bengaluru, and Mumbai all pass through those same resources. The services are separated by responsibility, but the users still share the deployment. The cell changes that second part. Instead of one production slice serving everyone, QuickBite creates several isolated deployment slices. Each slice contains the services and infrastructure required to serve a particular group of customers. That complete, bounded slice is a cell. This is the relationship people often miss. A cell is not an alternative to microservices. A cell normally contains multiple microservices. QuickBite can still have customer, order, payment, and delivery services. It now runs the required instances inside each customer-facing cell. Suppose QuickBite assigns Chennai customers to cell A, Bengaluru customers to cell B, and Mumbai customers to cell C. Each city now uses its own order service instances, queues, caches, and databases. The business capabilities are the same. The traffic and failure domains are different. First, return to the shared design. If the common orders database runs out of connections, every order service begins waiting. Checkout slows in all three cities. The failed component is one database, but its blast radius, the users who experience the failure, is the entire platform. Now fail the orders database inside cell A. Chennai may stop taking orders, but Bengaluru and Mumbai continue through their own databases and queues. Cells do not prevent the failure. They prevent one failure from automatically becoming everybody's failure. That smaller blast radius is the central reason cells exist. Here is a useful mental model. Microservices are rooms inside an apartment. The kitchen, bedroom, and living room have different jobs. Cell architecture creates several complete apartments. A plumbing problem in apartment A does not automatically make apartments B and C unlivable. Open the Bengaluru cell. It might contain an ingress, application microservices, service-owned databases, caches, message queues, background workers, and cell-level telemetry. The exact contents vary, but the critical request path must remain operable without calling another customer cell. Deployment control plane, global analytics, and sometimes authentication may live in a global layer. But every shared component is a design decision. If a global dependency fails, it can expand the blast radius across otherwise isolated cells. Customers still use one public QuickBite address. A routing layer reads a stable key, perhaps customer ID or restaurant ID, and asks the cell directory which cell owns it. Customer 42 belongs to cell B, so the router forwards that request to cell B. The partition key must be available early, stable over time, and aligned with most data access. If orders are owned by customers, customer ID may work. If operations are regional, city or region may work. A poor key creates constant cross-cell traffic and destroys the intended isolation. Now follow one Bengaluru order. The router selects cell B. Cell B's order service validates the cart. Its payment service begins the charge. Its queue schedules delivery work, and its database stores the order. The request does not wander through cells A or C. That last sentence is the rule. Cells should be independently operable. Direct cross-cell calls, a shared writable database, or one common queue reconnect their failure paths. The boxes may still be called cells, but operationally they have become one distributed failure domain again. The first benefit is smaller blast radius, including noisy neighbor problems. A restaurant importing millions of menu items can saturate the queue or database inside its cell without consuming the capacity reserved for every other cell. The boundary limits both failures and accidental resource monopoly. The second benefit is predictable growth. Instead of building one enormous cluster, database cache, or Kafka installation forever, the platform tests a cell's safe capacity. When existing cells fill, it creates another known good cell and assigns new customers. Cells can also support regional, regulatory, or tenant isolation. European data can remain in European cells. A major banking customer can receive a dedicated cell, while smaller customers share pooled cells. The placement boundary can reflect business and compliance requirements, not only scale. Finally, cells make progressive delivery natural. Release to an internal cell, then a canary cell, then 5% of the fleet. If errors rise, stop before every customer receives the bad version. The deployment blast radius becomes bounded just like the infrastructure blast radius. Put the architectures side by side. ICOM business, such as orders. A cells unit is one complete deployment slice for a traffic cohort. Microservices scale individual capabilities. Cells add deployment slices and then scale services inside each slice. In many microservice systems, each service owns a database used by all of its customers. In a cell design, that service usually has separate data per cell. Services can still deploy independently, but the platform must coordinate versions, schemas, and configuration across the entire cell fleet. Both approaches value automation during split interfaces. Independent Microservices is the containers primarily separate business beings realization fix. Cells primarily separate traffic, resources, and failure impact. Used together, they create a two-dimensional architecture. Cells scale at R4. Duplicate infrastructure and liferhead consistency, configuration, consistency, many data integrations, and cell-aware monitoring. Instead of operating one production environment, the platform operates a changing fleet of similar environments. Isolation is purchased with machinery. The hardest design problem is cross-cell data. What happens when a Bengaluru customer sends something to a Chennai customer? A synchronous cross-cell call weakens independence. A global service expands shared scope. Asynchronous replication adds delay. There is no universal answer. The product interaction must choose a trade-off deliberately. Capacity also changes, so customers sometimes move. A safe migration copies the customer's data, catches up changes, switches the directory assignment, verifies reads and writes in the destination, and only then removes the old copy. Until verification succeeds, rollback must remain possible. This is why cell platforms separate control and data planes. The control plane creates cells, assigns customers, publishes routes, and coordinates migrations. The data plane, the router, and cells serves live requests. Existing traffic should continue from cached assignments, even if management is temporarily unavailable. Cells become attractive when the platform has many users or tenants. The cost of a global outage is high. Customers partition cleanly. Infrastructure is approaching practical limits, or regional isolation matters. They also require a team capable of automating deployments, routing, observability, and recovery. For a small or medium application, cells can be premature. If one deployment is easy to operate, outages are tolerable, or requests constantly need global data, the additional fleet may create more failure modes than it removes. Architecture should pay for a real constraint, not imitate a large company. Most systems do not begin with cells. They evolve from a monolith to a modular monolith or microservices, then reach a large shared platform whose blast radius or infrastructure limits become unacceptable. Cells are often the next boundary added after those problems become concrete. So remember the two questions. What should change together? That is the microservice boundary. Which users, resources, and failures should stay together? That is the cell boundary. Put well-designed services inside well-isolated cells, and one broken component no longer has to become everyone's outage.